For today's agenda, we'll talk about the input filter stability problem, do an experiment, what happens if you have a badly designed input filter, how you can damp the filter and how does it look like in the measurement, input impedance measurement, first of all the modulation, how you can measure the voltage and how you can measure the current, what are the possibilities to do so, and in the end we will have a hands-on measurement. So I will now hand over to Florian, who will do the first part of this presentation.
Thanks, Tobias. Yeah, as Tobias already said, the topic is input filter stability today, and the input filter stability problem occurs or is caused by the fact that a DC-DC converter, as depicted here, we have the converter that is having a control loop with the loop gain T and the controller that acts on the converter. So a switching converter has a negative differential input resistance or a negative input impedance. That's quite, for me in the beginning it was hard to imagine, but it's pretty simple if you take this experiment, or if you think about it. If you have a DC-DC converter that is producing a constant output voltage, and if you increase the input voltage, then the input current will go down. It will consume less current. Yeah? An increasing voltage that causes a lowering current, that's actually a negative resistance, because a positive resistance would cause a higher current consumption if you increase the voltage. So that's the negative input resistance of a DC-DC converter, and this input impedance is depicted here as the Z-in of S, and if you have an input filter connected to the system that has some finite output impedance, then you have a negative input impedance. Well, then you can create a negative resistance oscillator. This principle is used to create oscillators, but in that case we don't want an oscillator, since the idea of that system is not to create oscillation. The idea is to have a DC conversion. So we don't want the negative resistance oscillation, and that's why we need to look at the input filter, design it properly such that this case does not happen. The input filter stability problem was described by Middlebrook, and he used the so-called Extra-Element-Theorem to describe that, and that shows how a transfer function in a system is changed when you add additional impedance to the linear network. So if we have our converter that has a transfer function that's a duty cycle to output, the GVD here, and then there is some impedance connected to it, in this case the Z out from the input filter, then the Extra-Element Theorem says you can calculate the transfer function GVD with the input filter connected by using the transfer function with zero impedance from the input filter, so a perfect non-existent input filter actually, and then you can multiply it with 1 plus Z out over Zn and 1 plus Z out over Zd, where the Zd, that's actually the input impedance of the converter with a constant duty cycle, and the Zn is the input impedance of the converter or of the transfer function with an ideal controller. So that means that the output impedance is constant. So the Zd, you could theoretically measure that in open loop. The Zn is not possible to measure. That's a purely theoretical value, because there will never be an ideal controller that rejects all the ripple at the output. So these are mostly mathematical expressions that you can use during a design process if you have calculated all the equations and all the transfer functions, but they are not so useful for an experimental approach as we are going to do it in this webinar. But there is the basic design criterion for the stable system that says if the Z out is a lot smaller than the Zn and the Z out of the filter is a lot smaller than the Zd, then this factor will be approximately 1. This means that the control loop will not be affected by the input filter that you can connect. As I said before, the Zn and Zd need to be calculated or simulated, but you could also apply a much simpler black box criterion that says the output filter impedance must be a lot smaller than the input impedance, the closed loop input impedance of the converter, and that can be measured. This condition that the set out is a lot smaller than set in ensures stability, but it doesn't guarantee that the system performance is unaffected. So the input filter might still degrade the system performance a little bit, but it will not cause complete instability or oscillation. So in this webinar, we'll now first show you the results of an experiment that we have conducted, and then we're going to show the results on a live measurement afterwards. Or first we show some experiment results, then we talk about how you can measure this stuff, and then we will do that in the webinar at the end. So we tried to measure it and to check does it really happen in reality, and for that we used a synchronous buck converter evaluation board that has an output voltage of 3.3 volts, and we did apply a load of roughly 10 ohms to get the load current of 300 milliamps. So that's the evaluation board that you can see here. Here is the circuit schematic. So that's the buck converter. It's a microchip evaluation board. So why could one want to add an input filter? Well, without an input filter, the current ripple at the input is very high. That's a problem of the buck converter. And in the picture below, you can see the input filter where there is a really high current ripple of several hundred milliamps. Yeah, that's pretty nasty. And with an input filter, so we designed a little input filter that has a 8.2 microhenry inductance and 10 microfarad input capacitance, and then the input current is beautifully flat. So that will of course cause a lot less problems in EMI, but we have seen that the influence of the filter affects the loop gain. So that's the loop gain of our control loop without an input filter connected. And when connecting the input filter, then you can see that the control loop changes. And at that frequency, we get an additional crossover and a strong change in phase. And this will cause, of course, an influence on the transient response as well. So the filter added a second crossover frequency, it reduced the phase margin, and we'll check out the step response next. So the small signal step response without an input filter or with a damped input filter, so a well-designed input filter, did look like that. There is a recovery and a slight overshoot, nearly no ringing, but when we added the undamped input filter, then suddenly there was a lot of ringing in the system, and the ringing was at 17 to 18 kilohertz. We can see that later on in the measurement as well. By the way, that was a small signal repetitive load steps, so roughly I think 40-50 milliamp load steps created with the J2111 current injector and an arbitrary function generator. And then we used averaging to get rid of the switching ripple, but we'll do that later on in addition. So why did that happen? And for that, we simply checked the impedance condition of the filter stability criterion. So the upper curves are showing the converter input impedance. That's of course a negative value. We didn't plot the phase here, but it's at minus 180 degrees. And when lowering the input voltage of the converter, the dynamic input resistance is going down, is dropping and dropping until it eventually did hit the undamped filter output impedance that has a very high peaking due to a very high Q in the filter. It's a ceramic capacitor and a nice low loss inductor, so the peaking of the resonance is very high, and you can see that resonance was at 17 kilohertz, exactly where the system shows a ringing in the transient response. So the filter LC input filter output impedance, so the impedance of the input filter can easily be measured. We're going to do that later on as well. And there are several possibilities to damp such a filter. So the green curve, that's the undamped filter that has roughly 12 ohms when it peaks at resonance. And then when you damp it, you can bring it down to 1 ohm. So get rid of the peaking. This can be done So in here again, the damping of the input filter that shows it still has some influence on the loop gain, but it doesn't cause the second crossover anymore, and the influence is rather small now. How is that done? There are two main approaches. The one approach is the RC parallel damping. That's also the one that we applied here. We're going to see that later. That is an additional DC blocking capacitor here and a damping resistor in parallel to the capacitor. If you have an ESR, high ESR capacitor, such as an aluminum electrolytic with a very high ESR, this might even be sufficient. In this case, we have used ceramic capacitors with a series resistor. The second approach is the RL parallel damping, where a damping resistor is added in parallel to the inductor. Of course, you don't want to have a series resistor in the inductor because that will cause a loss. It will damp, but it will also cause a high loss. So that's why the RL parallel damping is used. And yeah, if you have an inductor with a high ESR, that could be enough. So you might not even need an additional component as the resistor. There are several approaches to that. A lot of literature talks about optimal damping, how to minimize the size of the damping components. In the end of that presentation, you will see some references where you can look up some literature to optimal damping. So that's basically the theory behind the input filter stability problem, and Tobias is now going to present how you can use the Bode 100 to measure input impedance of a DC-DC converter.
Okay, let's go on. Now we'll show you how to measure the input impedance. What are the possibilities using the Bode 100? First of all, we use the voltage current measurement method within the Bode analyzer suite. You can see a picture here. How does it look like? Then the Bode 100 is already preset to do this measurement. The advantage of this measurement method is that it directly shows impedance results, so you can display the series inductance, the series capacitance, or whatever impedance value you want to show. It also offers the possibility to do a through or open short low calibration, and an arbitrary probe factor can be set within the hardware setup. Now, how does this look like? So the Bode measures voltage and current. So actually that's a gain measurement where channel 2 you get the voltage information, and at channel 1 you get the current. Voltage divided by current, that's impedance. So what do you need to do so? You need the, a possibility to modulate the AC signal on top of the DC input signal. You need an input current measurement, so a current probe or shunt resistor, we'll show that afterwards, and how a possibility to measure the voltage at the input. This is the hardware setup within the Bode 100. So the blue box is the Bode 100 itself, and these are the internal components that you can set. First of all, the attenuators to improve the signal to noise ratio. So if you get a high input signal, you can also add additional damping to your receivers, or if the signal is very small, then you can reduce it to 0 dBm. So the possibility is 0, 10, 20, and 30 and 40 dB attenuation at the receiver. Then the inputs can be switched between 1 mega ohm or 50 ohm. You can change the channel termination. For example, if you have a current probe at channel 1 which needs a 50 ohm input, you can change that within the hardware. And then you can use the arbitrary probe factor. So you can set it from 10 to 1 or whatever you have, or you can even use the negative value to invert the channel. So this, if you have a 10 to 1 probe and you have to set it on negative, then this minus 10 to 1 probe factor will introduce an additional minus 180 degree of phase shift, and then the value will be shown positive within the Bode analyzer suite. One more hint: the Bode 100 software, within the Bode 100 software, you can set, for example, the channels. but it is not directly set within the Bode hardware. So you first have to start a measurement, a single sweep or a continuous sweep, and then the Bode 100 will be configured. So how can you do the modulation of the input? So you have to do it somehow to put the AC signal, the AC output signal of the Bode on top of this DC input voltage of your input, of your voltage regulator. For there you can use specific devices, for example, the Picotest 2120 line injector, which can go up to 50 volts and 5 amps, or the high current injector, the 2121 high power line injector, which we'll use afterwards in our measurement, where it can go up to 400 volts and even 20 amps. You can use inductive coupling or capacitive coupling. As also be seen in one of the last webinars, in the output impedance webinar. To do so, we recommend to use an external power amplifier if you need more signal, which will give you a better signal to noise ratio to get more signal onto your DC line. For example, if you use the BM12, you get additional 12 dB, which is 4 times the output level of the Bode 100. These are the setups. If you use the Picotest 2120, you have the DC supply voltage, which is connected to the input of this line injector. You have the AC signal. This one will add these both signals together and put it into your device under test. Channel 2 is a voltage probe, channel 1 a current probe. And if you use the 2121, you do not need a current probe, because the 2121 line injector already does have a current monitor output, which is actually a current probe. So the advantage is it is really easy to use, but the maximum ratings are fixed. And if you use the 2120, there's a small DC voltage loss. Actually, there's also one for the 2121, but the voltage loss is a lot smaller.
And it's regulated, and it's always the same. It's something like 0.6 volts. On the J2120, it's not regulated, so it will change with the operating point. For the signal injection, you can also do capacitive coupling. That's the same like for the output impedance measurement. There's a the BM12, which is the amplifier. Then you have the DC block, and you capacitive couple the AC signal on top of your DC input voltage. You also need current probe and voltage probe. The advantage, this is scalable. So if you want to measure low frequencies, you can use a setup that is specifically made for small frequencies and, for example, small currents or small voltages. And you can do the same, scale it up use it for higher voltage or higher currents, whatever you need. The disadvantage is you may need an amplifier, and you have to use a DC block, which limits the lower frequency, or actually it's hard to get a very big capacitor so that you can use it at small frequencies as well. Then additionally you can use inductive coupling. So you have a transformer at the output, so additional the amplifier and current and voltage probe. This one is also scalable, exactly the same like for the capacitive coupling. Disadvantage might be the same. You need an amplifier most likely, and it is hard to get a right injection probe. So actually in the later picture we'll see one that we made ourselves, but I think it's not that easy to get one and to buy one which really fits the needs. Actually also really easy setup would be a power amplifier, but they are pretty expensive. So advantages are very powerful, fully configurable, depending on what you have. Yeah, disadvantage, they are pretty pricey. Injection method, a hint: if you inject a signal,
On the yellow, you can see there's an additional capacitor. This provides an additional low impedance path. So if you have the DC signal will flow to the power supply, which supplies the DC voltage current, and this capacitor adds an additional path for the AC signal. So the advantage is that it increases the injector signal size. You don't have to flow through the power supply. Then this improves the result, better signal-to-noise ratio because the signal bigger signal. And this will also enable you to do an open short load calibration because you do not need the power supply. So some possibilities to measure the voltage. Really easy, probably the easiest one-to-one connection, a BNC cable and 2 short leads. It's the price is very low, but there's no isolation, and also the noise is pretty low, depending on the cable length. If you use longer BNC cables, it will be better. You can use passive probes. This example, a 10-to-1 probe. Price, not that expensive, medium price level. Still no isolation, and the noise level is also medium. For active differential probes, they are a bit more pricey, so the prices are higher, but they offer isolation. So if you have higher voltages, please use them to protect the body and yourself, but you still get more noise if you use differential probes. To measure the current, either you use, for example, the 2121. There you don't need a current probe because it's already included in this box. Or you use, for example, Hall effect probes. In our case, it's an old Tektronix one. Important, it needs a BNC connector to connect to the Bode 100. They are actually really expensive, so high price. They offer isolation because there's no direct connection. The low frequency limitation, actually there's not really one because they can go down to DC, but the high frequency limitation are in the tens of megahertz range. DC sensitivity, they can be compensated. If you use an active Rogowski coil, current probe, price medium, they're not that expensive. They offer also isolation. Low frequency limitation, it depends on the probe that you buy, and high frequency also in the tens of megahertz. But there's no DC, they're not sensitive to DC, but there is no core. They can saturate, like if you use a current transformer, that's our self-made, actually Florian made that for this measurement. Price is also medium, depending on what material you use. They offer isolation, low frequency range depending on the core, depending on the windings that you're using. High frequency, also megahertz range, depending on how you build it yourself or what you buy. And they are DC sensitive because of the core. If you use bigger cores, well, not that sensitive, or the other way around. The last thing you can use is a shunt resistor. They are really cheap, but they offer no isolation. Low frequency limitation, there is none. Power and high frequency limitation also in the megahertz range. And they are sensitive to DC due to the power limit, otherwise they will burn or break at least. Okay, that's for the measuring examples. Now I will hand over to Florian, who will explain a little bit about calibration and how to verify your setup.
In general, it's always a good idea to verify the measurement setup, and for the input impedance measurement, you can use a known impedance such as a 100 ohm resistor or a 10 ohm resistor. You connect it instead of the DC-DC converter to the setup, and then you will see a positive 10 or 100 ohm resistance result, and that should be flat over the frequency range of interest, and then you know that the system or the setup is correctly, that you didn't miscalibrate it, or that you probably even don't need a calibration. When we talk about calibration, then please note that the Bode Analyzer Suite 3 supports either the Thru calibration or the open short load calibration in the voltage current mode. So you can either connect Thru calibration or open short load. In the Thru case, it will just calibrate the underlying gain measurement, because actually the impedance equals gain, where we said voltage at channel 2 divided by voltage at channel 1 is the gain, and if we give a current to channel 1, then the result will be an impedance. And for that you can use a 1 ohm resistor to perform a through calibration, because a 1 ohm resistor will have a gain of 1 volt is 1 amp, and 1 amp is 1 volt. This is very simple, you only need one measurement, and normally it's sufficient. The disadvantage is that at very high frequencies you might make a slight error that at 1 megahertz with a 1 ohm resistor you will have a 6% error, but actually that's not critical in that measurement. But if it's very important to have very accurate results, you could also do an open short load calibration, where you need to have an open, a short and a load connected. This is a full impedance calibration that offers the highest accuracy and the widest frequency range, but it's not always possible to make a short or an open, because you might need some signal for the current probe. So in open case there will not be any signal. You need to make 3 measurements. It's a little bit more tricky, and I would think about, is it really necessary that you have full calibration, or is the through calibration enough, or might you even be able to measure without the calibration if you don't need to go to the high megahertz range. So if we measure the input impedance of our device on the test, then it would look something like that, where we have the low frequency input impedance, and that's now the part where we have the negative resistance. And the negative resistance depends on the duty cycle and the load, because the load is reflected to the input, and in this case with a 10 ohm load and a 3.3 volt output will have roughly 100 ohms of differential impedance, and the phase would be minus 180 degrees, as we will see later on in the measurement. Then above, in this case 100 Hertz, the input capacitor is already dominating the impedance measurement. So that's a typical capacitor shape of impedance. So it falls with frequency, then it has a self-resonance, and after that there will be inductance from the trace and the parasitic inductance of the capacitor. The input impedance will depend on the input voltage. So if you change the input voltage, also the input impedance will change. In this case, it rises if you increase the input voltage, so it will lower when you reduce the input voltage. And another thing that we can see here, the input capacitor changes when the voltage changes. So in fact, the capacitance decreases when the input voltage is increased. And when we analyze that a little bit more in detail, so the 2 parallel 10 microfarad ceramic caps from that demo board, if you look at that, at 0 volts they have roughly 18 microfarads, at 10 volt 16, at 15 14, and at 30 volts, so the maximum input of that converter, they only have 7 microfarads instead of the nominal 20 microfarads. So if you plot that on the x-axis the voltage and on the y-axis the capacitance, you will see the typical degrading or the DC sensitivity of a ceramic capacitor. In this case it was a ceramic 10 microfarad, 50 volts, 1210 form, and an X7S ceramic. Please note that most of the ceramic capacitors, if they are not class 1, are highly sensitive to DC, so they will reduce, and in this case the 10 microfarad capacitor has less than 4 microfarads left at 30 volts, but it's rated to 50 volts. So let's go to our hands-on measurements. We have modified it slightly. We have taken off one of the capacitors, so it's now 10 microfarads instead of 20 microfarads at the input. And then we have a second device where we have added a beautiful input filter that is consisting of the 8 microhenry inductor and the 10 microfarad capacitor. This one also features an injection point such that we can see the influence of the input filter on the loop stability. First of all, we're going to measure the input impedance of that converter without the filter connected. The capacitor will stay there, but we don't have the inductor connected. Then we will measure the impedance of the filter that we have designed. So that's the 8.2 microhenry inductor and 10 microfarad capacitor. And we will then also add a damping network to the filter to see how that influences the filter impedance. Then we will measure the loop gain of the system without the filter and the transient response of the system without the filter. Then we will add the input filter, check the impact on the loop gain and on the transient response, and then we'll add the damping to see how the damping again improves the system. So, Tobias, the first thing we're going to do is input impedance measurement. Can you please set that up?
So first of all, we do have our two devices under test. So the top one where it's already connected to the line injector on the left hand side, so the input voltage, and on the right hand side is connected our load. So we can change the current that we want to draw. And on the top bottom side there is the second device under test, which is already connected with the input filter. But first we do the measurement without input filter. So I do have the line injector is already connected to the input. So I just have to connect the current monitor of the line injector to channel 1, the output of the Bode 100 to the oscillation input of the line injector, and last but not least I have to connect a voltage probe, which in our case is only a BNC cable, so 1-to-1 probe BNC cable with 2 leads. So that is one to channel 2, and will be connected to the input of our device under test. So that's it. So Florian, I think you can start and open the Bode Analyzer Suite.
Shouldn't we turn on the system and check if it runs?
I can do that first. Or if it blows up.
But the line injector needs power.
That one is not connected. Thank you very much. Now line injector is connected to power, and we can switch on the power supply. Okay, we have 8 volt input voltage. The output current is 0.31 amp, and the output voltage is also 3.2, like it should be.
Okay, in this case we can now perform the measurement. So we open up the Bode Analyzer Suite and go to the Impedance Analysis tab and select the voltage over current measurement method. In this case I'm going to load a file because we have already done a calibration to shorten that a little bit. So we have already done a calibration yesterday when preparing this session. So you can see the full range calibration is already done. It was a through calibration with a 1 ohm resistor. How did we configure the hardware? The receiver 1 probe was set to 10-to-1 because the current monitor of the J2121 is a 10-to-1 monitor, so it will give 100 millivolts per amp. The receiver 2 is set to 1-to-1 high impedance because we have directly connected the BNC cable to the input, so we don't have a 10-to-1 probe there. And on the trace 1 I'm going to show the magnitude of the impedance, and on trace 2 the phase of impedance, and now we can already start the measurement. So the measurement is already running, and we can see that we have an impedance of roughly 50 ohms in that load case, and the phase you can see is at -180 degrees. So I'm gonna put that into the memory. And can you please now lower the input voltage to 6 volts? That was 8 volts.
So now the input voltage is at 6 volts.
So now the input voltage is lowered, and also the input impedance has dropped. That's the 6 volts in and 0.3 amps out. And can you please go to 5? I think it should still run with 5.
Let's try it. Go down to 5 volts. Looks okay.
So now we are at 5 volts and the impedance has further dropped to roughly 16 ohms. So what's the minimum we can go? I think you can go to 4 volts in addition. Please try slowly.
Lower the input voltage a little bit.
I think that's too low. That's too low.
It was too low.
We have a 0.6 voltage, 0.6 volt drop in the line injector, so you will be able to go to 4.6 or 4.65, something like that.
Some 4.7. 4.65.
Okay.
It's still running.
And the input impedance has further dropped. So we can see at the low frequencies we see the DC portion of the input impedance, and at the higher frequencies we see how the input impedance falls with rising frequency. So that's the input capacitors. So now we know our input impedance, we can stop the measurement, and as a next thing we're gonna measure our input filter to check if we have an issue there. And you can now turn off please and take away the setup, and the next thing we're gonna do is measuring the filter that we're gonna add. Can you please also show the filter to the camera?
So I'll bring on the filter.
We have made a little second filter where you can see the inductor and the capacitor in the back of the inductor. So that's the LC filter. There is a ceramic capacitor and the inductor and the damping network on top that we can take off using a little jumper.
To do this measurement we use the B-wick, now connected to the Bode 100. Don't forget to put it in. So B-wick is connected. First, before we start the measurement, we need to do an open short low calibration.
Okay, so I'm gonna start a new Bode analyzer suite. For that I disconnect the device from that instance, and I'm gonna start a new Bode analyzer suite. And in that Bode analyzer suite I select impedance analysis and impedance adapter measurement. And we'll perform so we will measure from, what did we say? Roughly, I think the filter
100
is
Hertz.
100 Hertz to a megahertz or so.
Yeah, that's enough.
I think that's enough. And we're gonna do a calibration. I think a full range calibration is sufficient. Currently nothing is connected, so we click on to open and the Bode measures the open state. Now the BIOS connects the short calibration and I click on short calibration, and then we connect the load side of the calibration board.
So 100 ohm load on.
And we are done. And now we can connect the device and the test without the damping, please. So now the filter is connected, our device and the test, and we can start the sweep. So that's now the impedance, or actually the output impedance of the filter if it would be connected to an ideal voltage source, which we assume here. And you can see the peaking from the parallel resonance that is going above the 10 ohms in resonance. So we have a very high peaking. I'm gonna store that to the memory and call that undamped. And the peaking is at 18 kilohertz roughly. And now we're gonna damp the filter using an RC damping network, where you can see the resonance is now lowered by roughly a decade, so it's only 2 ohms then, or 1.8 ohms left. So that's the damped filter. You can see that the frequency response of the filter does not change too much, actually only at resonance it is influenced. And this damping network is a 44 microfarad capacitor with a 2 ohm series resistor. So now we know how we can damp the input filter to avoid the peaking. And if we look at the previous measurement, so when I switch to the previous measurement, then you can see that the impedance is coming towards 10 ohms if the input voltage drops. And the peaking of the input filter is going above 10 ohms in the undamped case. So that's where we do have the issue between the input filter and the input impedance of the power supply. And to show that issue, we're gonna do a loop gain measurement now and a transient response measurement. So Tobias, can you please change the setup?
So
let's get rid of that one.
So now we need the, I don't need that one, don't need that probe. So we now will use the second port on the bottom side, since there we already have injection resistor connected, so that I can use the do a loop gain measurement. So we'll connect the loads to the second port, and then we will connect input voltage from our power supply. And to do the loop gain measurement, now connect the output of the Bode 100 via the injection transformer to our injection resistor, which are these pins here. Now the only thing left I have to do is connect channel 1 and channel 2 of the Bode 100 to the injection resistor as well. That's my last connection.
Okay, so now we have set up the system for a loop gain measurement. We have increased the voltage because we know at higher input voltage we shouldn't face an issue, and we're gonna measure the loop now. So for that I have to again disconnect the device from that Bode suite and start a new Bode suite. And this time I'm gonna select the gain phase measurement. And I will run the measurement from 1 kilohertz to 400 kilohertz, because the switching frequency is at 400 kilohertz and the crossover frequency is around 30 kilohertz, and we know that the issue appears at around 18 kilohertz, so that should give me enough frequency range here. And yeah, I think that's basically it, and we can start the measurement.
I think you can switch off the attenuators at channel 1 and channel 2.
Yeah, I'm gonna switch off the attenuators. Probably don't need them, let's see. Then I'm gonna reduce the receiver bandwidth a little bit to get the more noise rejection. And then I can see that there is a little bit too much level, I think. Let's try to reduce the injection level to check if this discontinuity goes away. Yes, there it's gone. So now we have a clean result with sufficiently low level, and that's at 8 volts input. Let's see what the phase margin is. If we go to 0 dB here, we have a phase margin of roughly 50 degrees, and we can now look at the step load response of that system and check if it matches the 50 degrees phase margin. Can you please switch on the
load? I just need to switch on the waveform generator. That's wrong.
Is the Does it still have the right settings?
Yes.
Okay. Then you have a look at the scope. Can you please connect the scope probe as well to the output?
I'll do so now. Connecting the probe. This one is connected. Now we should see.
Okay, bring on the scope.
This is
We
Bode.
have to take away the Bode. That's sweeping in the step load response. Okay. So now we have the step response of that system, a small signal step load response, and you can see that it recovers quickly and there is no overshoot and no ringing on the transient response. So we're gonna go back to the loop gain measurement. Can you please connect the injection transformer again?
So
And then take off the load stepping, because otherwise our measurement will be pretty noisy. So now the load stepping is off and the measurement is running again. And now we know that we have no input filter connected. Yes, and now we're gonna connect the input filter. So there is a jumper on the input filter where that did short the inductor, and Tobias is now taking off the jumper to add the input filter.
So now the input filter is connected.
And nearly nothing did happen because we're still quite far away from any problems. We are at 8 volts input. The input impedance is very high and we don't have an issue at the moment. So there is a slight change here that you can see in this area. That's from the input filter. We do already know. But now we're going to reduce the input voltage slowly to check when there is going to really be a problem appearing.
Okay, so we'll now slowly reduce the input voltage. Now we're at 7 volts. 6 volts. A little bigger. Now we're getting to 5 volts.
So that's 5 volts.
Now that's 5.
Okay, 1 second.
Then
I think you should be able to go to 4 volts.
Yeah, 4.6 the
4. Got to 4.
voltage drop.
We don't have the line injector in anymore.
Yeah, exactly. Thank you very much.
Oh, I think that was too much. Can you maybe go
No, actually it's
a little bit higher, please, because I have an overload here. 4.1, something like that. Okay, there is an overload. I need to increase the receiver a little bit. So let's go to 10 dB receiver attenuators. We are at 4.1 volts. And you can see that the loop gain is starting to be corrupted at the resonance frequency of the input filter. That's 4.1 volts input and 0.3 volt amp out. Okay, so let's have a look how the transient response of that system looks now. So bring on the scope. Tobias, can you please take off the Bode sweeping and switch on the load stepping. Okay, there we are. And now you can see that there is a significant ringing that is very low damping. And the frequency of that ringing, I have already placed the cursors, is at 17.8 or at 18 kilohertz. So that's a ringing that is now not caused by the crossover frequency of the loop itself, or not by the properly designed loop. Actually, it's caused by the wrongly designed input filter that is now peaking so high that it causes a problem with the input impedance of the DC-DC converter. And now you can please put on the damping. I'm gonna bring you on screen again. Maybe I can make that not full screen. Is that possible? That we can see the result of the scope immediately. So yeah, you can see the result of the scope in the background.
Now we'll use connected.
And Tobias is connecting the damping network, and the ringing is now nearly gone. So let's have a look at the loop gain measurement now. Please take off the load stepping and bring on the connection to the injection transformer. The measurement is running, and you can see that in the frequency range where at the 18 kilohertz, we don't have the big issue anymore. The loop gain curve is still a little bit influenced by the input filter, but it doesn't cause the very low degradation of the system performance anymore. I think, did we forget something, Tobias? Let's have a look at the slide. We said we're going to measure input impedance. We've done that. We're going to measure the filter impedance. We did that. Measure the system dynamics without the filter. We did that. Add the filter. We did that. And we did damp the input filter. So I think that's it from our side. If you want to read more on that, if you want to read where does it all come from, who invented all that stuff or found it out or wrote it down the first time, there are some references on that slide.